Now let's talk about the causes of irreversibility. There are two main causes. The first one is the lack of equilibrium during the process, and the second one is the involvement of dissipative effects. We will look at them one by one. Now let's have a look at the first one, that is the lack of equilibrium during the process. Now, the lack of equilibrium, the equilibrium can be mechanical, it can be chemical, okay, or it can be thermal. So lack of any equilibrium out of these three, between the system and the surroundings, or between two systems or two parts of the same system, causes a spontaneous change which is reversible. Okay, so let's have a look at one example to actually quantify the first cause of irreversibility. And the first, or the example to quantify the first cause is, let us name this A, or let us say a capital A in that case, because you have the two figures named as small a and small b. So the example in this case is heat transfer through a finite temperature difference. Through a finite temperature difference. Alright, to understand this, let's have a look at the two figures, that is figure A and figure B. Let's start with figure A first. Okay, so you have two temperatures, so two temperature reservoirs, that is TA and TB. So we can assume that temperature of A is higher than temperature of B. Now this is the case, you have a certain amount of heat being transferred from A to B. Okay, so this is what is happening. So let us assume that this is the source and this is the sink, and you have QAB as the amount of heat that is flowing from A to B. So this is how the heat is flowing. Alright, now let's assume a heat engine which is operating between A and B. So this is the heat engine E, right, and it is taking Q1 heat from A and discharging Q2 heat to sink B, and in the same process you're getting some network output. Now if you come to figure B and you reverse this heat exchange process, or you can reverse this heat transfer process, and now you have heat flowing from B to A. So the arrow is reversed in this case, you have QBA, and the heat engine is working in such a way such that whatever heat that is being rejected, the same amount of heat is being carried to the source TA. Okay, so this means that the heat engine, this heat engine is working in such a way such that Q2 is equal to QBA. So if this is the case, it eliminates the requirement or the necessity of the sink. You can remove this sink because whatever heat is coming, that is being rejected from the engine, it is directly being fed to the thermal energy reservoir A. Okay, so if you remove the sink B, the net result is a cycle which is only exchanging heat with A. So it violates the Kelvin-Planck statement. Okay, so this brings us to a conclusion that the heat transfer QAB, this is a spontaneous change. So this is an irreversible process, and because if you reverse this heat transfer direction QBA, so in this case the Kelvin-Planck law is being, or this statement is being violated. So this is not possible. This is not possible at all. Alright, so this again brings gives us some very important conclusions. So this is the proof, or you can say demonstration with the help of second law, that heat transfer through a finite temperature difference is irreversible. Right, so if you summarize this demonstration, you would say that a heat transfer process approaches a reversibility as the temperature difference between two bodies approaches 0. Okay, so you can say the heat transfer, it approaches reversibility as the delta T approaches 0. Because if you remember, we define a reversible process as a process through which heat is transferred through an infinitesimal temperature difference. Now, so to transfer a finite amount of heat, so this is a finite amount of heat, okay, through an infinitesimal temperature difference would require an infinite amount of time, and if the requirement of time or the time required is infinite, it automatically becomes reversible. Okay, so all actual heat transfer processes are through finite temperature differences and are therefore reversible. Okay, and higher the temperature difference, the higher is the irreversibility. Okay, so you can say that delta T increases, it increases the irreversibility. So this is a very, very important concept to understand. Okay, so I hope this is clear. That is the irreversibility due to lack of equilibrium, and we demonstrated it with the help of the example in which we said that the heat transfer through a finite temperature difference is always irreversible. Okay, now there are some other examples also that you can go through at your own, for the lack of equilibrium to produce irreversibility. Okay, I'll just put them down on the screen. So the second example you can read about is the lack of pressure equilibrium within the interior of the system or between system and surroundings. So if you have, I'll just write it down, lack of pressure equilibrium. So whenever you have some pressure differences, you will have some spontaneous changes. Alright. The next one is again a free expansion process is a spontaneous process, thus an irreversible one. Right. So now after this, let's understand the second cause of irreversibility, that is the involvement of dissipative effects. Now the irreversibility of a process may be due to the dissipative effects. Now what are these effects? Let's talk about these. In dissipative effects, the work is done without producing an equivalent increase in the kinetic or potential energy of the system. So if this is the system, you do some work, alright, there is no increase or there is no change in the kinetic energy and the potential energy of the system. 0 and 0. Okay, and whatever work is done that is transformed into the molecular internal energy is due to effects like friction, okay, viscosity, or you can say resistance, and this resistance is the electrical resistance. Okay, so all these phenomena, they produce the irreversibility due to the dissipative effects. Okay, now let's understand how does friction and electrical resistance create irreversibility in a process. So let's start by understanding the irreversibility due to friction. So this would be the first case. So for this, let's draw a diagram. Okay, so a diagram would be like this. So let's draw a hypothetical flywheel like this. Okay, and let's put a brake block like this. So this is the brake block. Okay, so this is the flywheel, and this is the brake block. Okay, and you are applying some force over here, and this is rotating in this direction. Alright, now if you talk about friction, now friction is always present in moving devices. Okay, and friction may be reduced with the help of some lubrication, but it can never be completely eliminated. If this were possible, a movable device could be kept in continual motion without violating either of the two laws of thermodynamics. Okay, so if continual motion, or you can say continuous motion, or the same thing, if the continuous motion of a movable device is there, is possible or occurs or is present, movable device is there in complete absence of friction, because we just talked about that you cannot eliminate it completely, but you can only reduce its amount of friction that you have. So there is so the continuous motion of a movable device is there in a complete absence of friction. Alright, so this kind of a motion is called the perpetual motion of the third kind. So this is very, very interesting to know that you have a PMM3. So if you have a machine or a device which can function continuously without friction at all, so you have absolute absence of friction, then this kind of a machine is called a PMM3. Now, the friction makes a process irreversible. Okay, now we'll demonstrate that with the help of the second law. For that, let's consider a flywheel in a brake block system. So this is what we will consider, and let us isolate this. Let's make it an isolated system. So let's put it in a hypothetical isolation. Okay, so like this. Alright, now the flywheel, that is this flywheel, it is rotating at a certain RPM, and it was brought to rest by applying the friction brake. So this is the friction brake and this is the brake block. Now the distance moved by the brake is very small, so this distance which the block moves to stop the brake is very, very small. So the work transfer is almost zero because the distance is very, very small, because work is usually FDS, so it's very small, so the work is zero. Now if the braking process occurs very rapidly, very rapidly, the heat transfer is again zero, or you can say it is almost zero, it's very little. So in this process, let us say 1, it indicates before braking, and 2 indicates after braking. Okay, so if you apply the first law in this process, that is the process of braking, the heat transfer in going from 1 to 2 is equal to the change in the internal energy plus the work done in going from 1 to 2. Now we just talked about that the Q is 0, and because of small distance the work is 0. So we will have E2 is equal to E1. So this is a very, very important observation in this example. Okay, that is the internal energy remains constant. This means that the system is isolated. Okay, so let's write it down. So this means energy remains constant. Okay, now since the energy may exist in the forms of kinetic, potential and molecular internal energy, so we can apply the steady flow energy equation in this. You will have U2 plus, or you can say U1 plus, you will have mv1 square by 2 plus mz1 g is equal to U2 plus mv2 square by 2 plus mz2 G. So this is the steady flow energy equation. Now, because we are bringing the flywheel to rest, so you can say that the final velocity would be 0, and there are no elevation differences, they can be cancelled off, and we will get the equation as u2 is equal to u1 plus mv1 square by 2. Now how do we interpret this? So this equation tells us that the molecular internal energy of the system being your brake and your flywheel, it increases by absorbing the kinetic energy. So whatever kinetic energy you have, you add it to the present molecular internal energy, so it gives an increment to this energy and it becomes u2, right? But if you take the reverse process, that is, if you convert this increment, okay, of the internal energy into the kinetic energy within the system, so it causes the wheel to rotate, it is not possible, right? So this is a very important consideration over here. So you say that your wheel is rotating, okay, it rotates, and then you apply brakes, all right. So whatever kinetic energy it had, it increases the molecular internal energy, and so this is what we get. But now there is an increase in the energy and it is stored in the flywheel. Now if I start, or if and suppose if I use up this increase in the energy, I cannot make this wheel to start rotating. So this is again a case of, I can say, a directional preference of process being feasible or not. So the feasibility is there that you apply brakes and you start or you stop the flywheel from rotation, but if you put back the energy, again into the brake, you cannot make the flywheel to start rotating again. So this is a directional preference that we talked about in the introduction to the second law, right? Now we need to prove this with the help of second law. So let us assume that the reverse is possible, okay, and the reverse being that the conversion of the increase in the molecular internal energy into kinetic energy within the system will cause the wheel to rotate, right? So let us say this is possible, and imagine the following cycle with 3 processes, and these processes are process A, B and C. So you'll have process A, then we'll have process C, B, not C, process B, and the next is process C. So we'll have these 3 processes and we'll analyze them one by one. Now let's take the case of process A first. Now process A says that initially, let us say the wheel and the brake are at high temperature, which is the result of the absorption of the kinetic energy of the wheel. Okay, and the flywheel is at rest. So the process A is the condition of the system after the braking is complete, right? So after the braking is complete, the temperature is high, and the flywheel is at rest, okay, because the flywheel and the brake system has, or the flywheel and the brake, they have used up the internal energy of the wheel and the brake. And now what happens is that at this instance, let us say the flywheel starts to rotate at some RPM. Now when the flywheel is at rest and the temperature is high, this indicates an increase in the internal molecular energy that we talked about. Okay, now when the flywheel starts rotating, it does so at the expense of the internal energy of the wheel and brake. Now when the internal energy is being used up, the temperature would reduce, but obviously, okay. Now let's come to process B. Now process B is a continuation of the process A, which says, so as you start rotating the flywheel, okay, and let us say the work is being done to do some redundant kind of work, so it creates no change in the temperature. So the flywheel, right, so whatever work is being done, it is being done to do some redundant work, and this internal energy increase, this internal energy increase, which which creates the flywheel to start rotating. So after that, you can say the flywheel expends all the energy and comes to rest. Alright. So in doing so, there is no change in the temperature. No change in temperature. Alright, so what happened is, in the process A, the flywheel was at rest. It starts to move, okay, by some by something which started using its internal energy, and the temperature started to drop. In process B, it was brought to rest, alright, by doing some redundant work, and it brought no change in the temperature. Now in the process C, what we will do, we will now supply some heat from some source to the system, that is the flywheel in the brake, to restore the system to its initial state. Okay, so now we are supplying the heat to the system, okay, to restore it to initial state. Now, how do we depict this in the form of a diagram? Let's have a look. So let us say the system, that is your brake and the flywheel, it is this, and it is in the process A is at high temperature, so I can say that it is at temperature T1, and there is another source which is at T2. Alright, so this is T2, and we always assume that T1 is higher than T2. Right, now at this instance, this system is at rest, okay, and the temperature is high. So it says that it starts to move. When it starts to rotate, right, this means, let us say this is the engine, or this is the device that will use up the heat that comes out of this system. So this is Q1 that comes out of it, and you get some work output. Now in this process there is a decrease in its temperature. Now to keep the temperature constant, we will supply heat from another source, and that is, let us say, T2. Right, so if you look at this arrangement, there is no heat rejection. So this is a case where the system becomes a perpetual motion machine of second kind, which violates the Kp law or the Kp statement. So the braking process, that is the transformation of kinetic energy into molecular internal energy, is irreversible. So that is what we said in the first place, that is, only this is possible, the reverse of this is not possible. So this is an irreversible process. And how did we define it, or how did we prove it or demonstrate it? Like this. So you have this, that is, after braking, let us say the system temperature increases, okay, and your system is at rest. Now you start consuming that high energy or that high temperature, and you start taking out some heat from it, which starts the flywheel to rotate, okay, and that rotation can be used up to perform some work. There is no heat rejection, and because the temperature starts to come down, you start supplying heat from some other source to maintain the initial state of the system. So this eventually becomes a PMM2, violating the Kelvin-Planck statement, which is not possible. So the reverse of the braking process is not possible. Okay, so this was the first example of the irreversibility that comes into picture by the dissipative effects. Now let's briefly talk about the second case. That is, let us draw a line over here. And this case is the dissipative effects with the or via the electrical resistance. So let's talk about the irreversibility due to dissipative effects of electrical resistance. Now to demonstrate this concept, let us draw a resistor. It's a very easy concept to understand. So let us say we have a resistor like this. Alright, and this is getting some charge from this side, so some current is flowing. Okay, now the flow of current, it represents some work transfer, because that work transfer can actually drive a motor which can do some mechanical work. So due to the flow of current, you will have some work input. Okay, and due to this work input, you will have some heat rejection. Now taking this wire as a system, so this wire and this resistor as a system, and let's write the first law. So you can say that the heat interaction is equal to the increase in the or change in the internal energy plus the work interaction. Now in this case, both of these quantities, work is negative because it is being supplied to the system, and the heat is negative because it is being rejected by the system. So both are negative. So this would be written as W12 is equal to U2 minus U1 plus Q12. So this is the appropriate way of writing the equation for condition in which a current is flowing through an electrical resistor. So this means a part of the work transfer is stored as an increase in the internal energy, and the rest is dissipated as heat. Now at steady state, the internal energy and hence the temperature of the resistance becomes constant. So and because current flow is a function of time, so at steady state the current flow becomes steady. There is no fluctuation of current flow with respect to time. Therefore the temperature also becomes constant. So the delta U value becomes 0 because U is a function of temperature, isn't it? So this becomes 0. So the equation is reduced to this. So whatever work that we supply is converted into equal amount of heat. So whatever work you supply, everything is then rejected as heat. Now the reverse of this process, that is the conversion of this heat into an equal amount of work, that is the electrical work, is not possible. Let us assume this is possible. Now if this is possible, then the heat, which is Q12, will be absorbed and an equal amount of work will be delivered. Okay, so if this happens, it becomes a PMM2. So if you talk about this, so this is the source, okay, and this is the, let us say, motor. So whatever heat you absorb, you get equal amount of work. So if this happens, it becomes a PMM2, which again violates the Kelvin-Planck statement. Right, so this means that the conversion of electrical work into the heat dissipation is possible, but the reverse, that is the conversion of heat into electrical work, is not possible. This means that the dissipation of electrical work into internal energy or heat, it is an irreversible process. Okay, so this is how we demonstrate the irreversibility caused due to the electrical resistance. Now this finishes this long video on the causes of irreversibility. I hope you understood this. Okay, now in the next video, let's move on to a very important cycle, that is Carnot cycle.